Hi everybody. Well, here we are. It is the first time I'm making a video in response to a snow day in Maine, but that's life, I guess. I hope you're all warm. I hope you're all cozy and indoors enjoying like a hot cup of tea or something like that. And this format, it offers us a few things that in-person learning doesn't, although I'm much more a fan of in-person learning. One of those things is that you can stop and start me at your will. Go ahead and replay things instead of asking me questions in class. Perhaps speed things up or slow down. Using YouTube's playback controls, all of that. And if you do have a question for me, you can always email me with a timestamp and say, "Hey, Lewis, at 4 minutes and whatever, so and so seconds and minutes, I don't quite understand what you were getting at there." So you can also point to specific things this way, which is really nice. I will ask you to do one thing though when we're doing these videos. Take care to not speed through them. A lot of people, I think, sometimes get this idea that they can just like skip to the end and, make the patch that they see on the screen at that point. I'm going to emphasize, take your time to really step through this and listen to the explanations, because if you don't, I'm afraid you're just not going to really learn how it works, how the stuff is put together, and you won't be able to like show that. You won't be able to do something creative with it later if you don't kind of understand the mechanics of it. So just treat this as if you would treat another in-person class, or the way you treated the other videos that we had. We may occasionally have more of these videos, but nevertheless, that's my little intro spiel. Why don't we get to the patching? So what you see in front of you is just a little illustration I made real quick of the purpose and the kind of structure of what we did last time. The getting started stuff, the scaffold. So we made this over here, right? We made a scaffold patch, which includes two major components, a sub-patcher for input and output. Actually, they're abstractions. They're not sub-patchers, just to be diligent and rigorous about the meaning of those things. So this is literally a patch that lives on disk, and it is on our folder. We call that an abstraction. And as you can see, they are connected in some way to whatever we're doing in any particular week, really, a working patch of some kind. And they are done this way through corresponding send and receive objects. So there isn't a physical connection here. There isn't a patch cable like you see in the patches. Instead, envision that the scaffold patch and the working patch are just two separate floating windows on your screen, and they communicate with each other via these send and receive pairs. There's a corresponding send and receive for each one of these things, as you probably already have guessed, but that's nevertheless how it works. And if I just minimize this for a second, here is a version of what we did last time. Here's the scaffold patch that we made in the Composing Sonic Systems class, and a sort of a simplified, incomplete version of the working patch that does all this work for us. So if I just, for example, open up the sound input, the input patch, you can see that it terminates here in the send in one, and its corresponding receive object picks up here in the working patch with a receive object that has the same argument, in one. So it really just depends on how you name these things. In one here, in one there. You can basically connect things without a physical cable. And likewise, the working patch terminates in two send objects that are named accordingly, and they're picked up here in the out patch. If I just pick this up, here we go. We have a receive pair and a corresponding send pair. So the working patch is designed to do some form of processing. The output patch receives it and transmits it to our speakers. Just a bit of review there. And in case it's not clear, what we're actually doing in this very simplified working patch idea is all we're doing is we're taking one signal and splitting it evenly across two different loudspeakers. We're taking a monaural signal and making it into a stereo signal that's evenly split. And we do that by scaling, using this scale object. We actually decrease the volume by 3 decibels for a very specific reason, actually, that has a lot to do with the inverse square law. We can get into the details of that, but for now, just know that if we lower the volume a little bit by like this amount, 3 decibels, and this is converted, as you can see here, into a linear representation of what decibels is, then we can get the same amount of sound pressure from here out to 2 speakers here. So we're just basically decreasing the volume a little bit and scaling it, and then sending it to our outputs. And we know this is connected and working. We can test it verifiably so by just sort of opening the different windows. And if I choose a sound, like for example, the noise form, this is white noise, and I just remember you see the metering here, but that's just the input. If I raise this meter, we'll see the sound coming out of the input patch here, being sent over this connection. And there it is. We have signal being processed over here, and then finally being picked up and received in the output patch. And that's all we really need to know. We know everything's connected right. If I, for example, close my working patch, if I just X out of it like that, I'm basically breaking the connection between the input and the output patch. If I raise the volume, you see metering on the output side of our first patch, our input, but then you see nothing received over here in the output patch. And why is that? Well, the thing connecting that, like sort of like another rung in the ladder or in the circuit, is that working patch. So if the working patch is closed, you will not hear something. Inevitably, something will not reach the output patch. That's what it's designed to do. So just want to let you know that that's kind of the idea here. I'll go ahead and switch this back to none. And we can close these. Remember, we can close these input and output things because they already live here. Just make sure your scaffold patch is like open and kind of functions as another little floating sidebar along with your Max console. If you don't see the Max console, remember that you can always go to Window Max console to toggle that on or off. It's important that you have it so that you can see like error reporting and stuff. Okay, so nevertheless, why don't we continue on here? Here's a week 2 folder. There's our work represented from that last little bit of excursion that we had last week. I'm going to create a new folder here on my desktop, or not on my desktop, excuse me, but inside my class folder. So in this case, I'm working in the Composing Sonic Systems, but Blueprints people, feel free to take care of this in your Blueprints folder. We're still kind of working on some of the same introductory material. So I'm going to create a new folder inside of here. I'll just control click here, add new folder, and of course, I'll name it accordingly week 3. And we'll build our stuff in here for the week. But of course, we'll keep our scaffold patch from week 2 open. The purpose of what we're doing today is to talk about basic waveforms that we can use to shape timbres and pitches and all kinds of exclusively fundamental musical material, we should say. So let's go up here and make a new patch. File, new patcher. And I'm going to immediately save this. Command S on Mac. And what I'll do is navigate to the proper place. Here's my week 3 folder. And I'll go ahead and title this accordingly. You can, again, choose your own variations, but I'll call this 1 Basic Waveforms. And if you want to version it, you're certainly welcome to. But, of course, Git does a lot of that versioning for us. So here's my working patch for the day. Now, the idea here is to learn about, or at least experiment with, basic waveforms that you may have seen or even heard in other programs and build synthesizers out of them. Let's make a few of them here. N for new object. I'm going to make an object here called cycle again, and notice there are 2 different versions. There's one that's just cycle, and then there's this one, which has the tilde sign on it, and that tells you that it's actually going to produce audio samples. It is the audio rate version of the cycle object, and it's a sinusoidal oscillator, very basic. So this object, let's give it an argument of 440 with a dot. You need to specify a decimal place number, a floating point number in Max with the dot. It's kind of old school. And we'll just press enter. Now what I like to do, because these are objects that create sound that we can listen to, and they don't pass signals that are used to control other objects, or at least not in this case, I'm going to open up the inspector. Remember that shortcut I showed you, Command I. As long as I have that object selected, I can open up the inspector and I get this long menu. I'm just going to change the color. We can start playing with some colors here. So I'm going to choose border color, and again, this is more of like a convention that I like to deal with. I'm going to choose standard palette of colors, and I'm going to choose like a nice red. And the reason I'm doing this is to show these red objects are going to be the ones that are producing audio signals that I can listen to. like they have volume that I'm going to hear. If I want to view what's actually coming out of the cycle object, I can create this object called scope with a tilde. And when I plug it in, I get a lot of crazy lines. I might just reshape it a little bit. And you might notice that this is really just a waveform going up and down. We'll change the shape of it later, but suffice it to say, this is how we can view the time domain representation of the signal. Just the waveform that describes displacement, magnitude, essentially amplitude and volume. It's showing you fluctuations in sound pressure. Underneath it, though, I'll have another view of this. If I type n again, I'll make another sort of representation of the signal by typing not scope, but spectroscope tilde. And if I tap the same output from cycle, I get the spectral view of the signal, or the frequency domain view. By the way, I should just give you these things so you know what they are. Here is the scope object. Here is the spectroscope object, in case you wondered what I was doing. Time is going from left to right, and sound pressure is on the y-axis. On the other hand, with spectroscope, the thing that goes from left to right is not time. In fact, time is not really represented here, but instead frequency. Low frequencies on the left, high frequencies on the right, and this continuum of frequency space along the x. And then what you see here, as you might know, is amplitude or loudness. So right now I have a cycle waveform, a sine wave of 440 hertz, and I essentially have one peak here at 440 hertz. And that's what I expect to see here. Two different forms of the same thing. Now you might also notice that the cycle object, which is making this sound, has two inputs, right? There's this one, which is a phase input, and the one that's most important for us really is this one, the frequency input. Frequency input we can control with a number. We could put like a floating point value in here with the F box. And if I change this, for example, if I make it really a low frequency, then you can really see the peaks and the valleys in the waveform. And you can actually see the fluctuation in amplitude when the waveform is very low, when the frequency is very low. If I return that to 440 hertz, because this number in frequency essentially replaces the argument that you initialize the object with here, well, you don't really see the bobbing up and down so much, and you don't really see the individual hills and valleys so much, just because the frequency rate is high. Now, we'll listen to what this sounds like later, but I want to just put a few different things on the page, and then we'll listen to each one of them. Another thing I want to specify is that this value, the frequency value, doesn't have to be hard-coded. So instead of the little F box, and by the way, this was just, I typed F, one of these little floating point boxes here. We don't have to hard-code it or change it dynamically with a simple float box, but we can also use our send and receives. So if I make a new object and just put R here, well, this is the receive object, but it's for numbers and not samples, not audio, but instead data. So remember this control paradigm I was explaining in that first video? The slower data rate or control rate is exactly what this R represents. We're going to be passing numbers individually when they are sent at a very slow queue. And I'm going to name it. I'm going to give this receive object an argument of freak, which you can name these anything you want, but I'm going to name this freak for frequency. I'm just going to put it in like so. And once again, I might Command I and just give it a color. So for these sorts of sends and receives, I might use like a blue. I just try to do things somewhat consistently so that it's easy to see information flow in the absence of patch cables. So the idea is I can control this from some other location. If I duplicate it, Command D, and put this somewhere else in my patch, and say change the R to an S for send, again I get my data rate send. And somewhere else in my patch, I can put one of these little float boxes like I had before and hook it up here to the send object. And then when I change this value, look at that. I've got 9.6 hertz. In this case, it's hertz. I'm sending it through this. It's being received over here without a patch cable, and it's going down into my cycle object, and I'm seeing the result of that. I've seen the shapes and and the rate of frequency change in my view objects. So just know that we're going to be making extensive use, actually, of these kinds of tools, the sends and receives at both audio rate and data rate. And we'll need this later. I'm just going to keep it down here for some amount of time. But let's look at some other waveforms. So we have this cycle object. Why don't we start recycling things? I'm going to just unlock the patch, highlight that whole block, and I'm going to duplicate it. Now, I'm sorry, guys, I forget what the Windows shortcut is. I'm going to always kind of speak in Mac terminology, but Command D will just duplicate anything that you've already created, or selected, I should say. Let's change this. The only thing I'm going to change in here is I'm going to double click inside my cycle tilde object, and then double click on cycle itself. And without eliminating that tilde that you see I don't have selected, I'm going to change this to a tri waveform, which you can see is described as a triangle oscillator of some type. If I go ahead and play it back, you can see the result I get is very different. Now, part of why this is different, I've initialized the object at 440 Hertz again. So if I want these to reflect the same frequency value, I'll just move the value down here in the number box again. And that's updating or sending the same value, 10.01, here and here. And now I can be sure, you can kind of see they look a little bit more in sync. The waveforms are progressing from left to right at the same rate, and I see more of the cycles of the waveform this way. So, hey, look at that, a triangle waveform and a sine waveform, which is more smooth. Again, we'll hear the consequences of these waveforms momentarily, just visually putting things on the page now. I'm also going to just grab this tri thing, and I'm going to stretch it out, because look, I have two more inputs. And let's create receive objects for this. We'll learn how to control this with more values in just a second, but for the moment, let's just grab the frequency and duplicate it, and change this from freak to something called duty cycle. I'm going to say duty.cycle. And I'll open up the inspector, change the color, maybe to a nice green. And I'll connect it here where it expects a value for something called duty cycle. And we'll define that in just a moment. Let's also create a receive tilde object, the audio rate receive form of the receive object, I should say, and we'll call this one sync. I'm going to open this up, and I'll select like a purple, because why not be colorful? And I'll plug this in here. Notice that the patch cable is striped. It is an audio rate patch cable to go with the object with the tilde. So these are two different forms of the receive object. And I'm going to use, as you might guess, something coming through here to synchronize the waveform, and something else here called duty cycle, which will become clear momentarily. For now, though, just notice the difference in quality of these waveforms. And if I, for example, increase the value of my frequency so that we get into the audio range, if I actually blow this up a little bit farther, let's make this, roughly 700 Hertz or so. Notice the difference here in the spectroscope. You've got one peak, but here, with the triangle waveform, you have many peaks. We'll discuss why that is and hear it in a moment, but that's a little bit of an illustration visually about the difference in shape. Let's continue on. I'm once again going to highlight this entire block, and Command D, put it over here, and instead of triangle waveforms, instead I'm going to highlight tri, and change it to SAW, S-A-W. You can see it's a sawtooth waveform if you look at the autocomplete. And once again, I'm just going to press enter there. And notice that there's only two inlets here, so it broke the cable with my receive tilde object. I'm going to go ahead and delete that. We don't need that in this case for the saw wave. Once again, we have a different frequency here. We've initialized this at 440, and then over here we have, what is it, 700 something, 17. But let's finish making things. I want to get to the listening part. I'm going to just make this patch a little bigger. If you notice what I did there, I just grabbed a corner and spread it out a bit. Let's also duplicate the triangle wave one more time. I'll highlight this block and duplicate, put it next door. And this time, instead of try, I'm going to say rect. That's our shorthand in Max for an anti-aliased rectangular or pulse oscillator, it says it's sometimes called. And when you initialize it, notice we do have that third inlet, the receive inlet. So this will behave somewhat like the triangular waveform. We have just a couple more that we should do. So here, maybe since it's 2 more, just make this a tad bit bigger. All right. Now this one, I actually don't think we need to, we actually won't need receive objects for, but instead just highlight the bottom portion of one of these guys here. So see what I did? I'll do it one more time actually. I'm going to highlight just these 3 objects and duplicate. And the reason we don't need these will become clear momentarily. I'm going to change this entire thing in the red box to noise with a tilde. And actually, I do have an inlet, and I can control the noise object with a couple of things, but we're not actually going to use that. I rarely control the noise object. It's just a white noise generator, as you might recall from last week. But let's highlight this once again and duplicate. And next door, we'll change this one from noise to pink, which, unlike the other object, is a different kind of noise generator. This is so-called pink noise. And you may see that it does look a little bit different. Now, we won't control the frequency of these objects. We don't really control frequency of noise because it represents the energy at all different frequency bins. And that means we're not specifying a specific frequency for either of these noise objects. Again, we'll define these more rigorously in a moment. We've left a little room at the top for some definitions. But how do we hear these things? Well, if I want to mix these things together or add them together, I need another object to plug these into. Down here, I'll make a new object and I'll type matrix with a tilde. I can just arrow down to the third option there or type it out myself. Matrix functions as a mixer. And a mixer, as you may have seen, has a number of inputs and outputs that can be patched and repatched together in different combinations. So not everything is sounding at once that comes into a mixer. Instead, you pick and choose, usually with buttons and faders and sliders and all sorts of stuff, what you hear at any different time. And the reason I'm making this is because of all the waveforms you see here, we only want to listen to or specify them one at a time, maybe in pairs. We can put them in any combination we want. But essentially we have 1, 2, 3, 4, 5, 6 different things we might want to hear, and we'll imagine those as inputs to our mixer. So I'm going to give some arguments here. The arguments, as you see listed, are the inlets and outlets of the matrix object. So I have 6 things I want to potentially hear as inlets or inputs. So I'll put a 6 there as my first argument. And my last argument, you might think, well, are we going to have 1? No, actually, let's go ahead and make 3. And I'll tell you why. I'm going to put 3 here. We'll tell you why in just a second. But let's cable this up. What I'll do is take this object and just spread it way out, maybe till about there, and I'll start plugging the individual waveforms into the individual inlets of my mixer. In fact, here I'll just I like to line things up so they look kind of good. This won't work well for all of them, but you can see there's a number of them. There's precisely 6 of them. Here, it's not going to look totally clean, but that sort of works. Kind of gets them in the middle. Now, all 6 things are coming into my mixer, and we have 3 outputs. Remember, we have 2 outputs, though, for our speakers. We have left and right, and remember which ones those are. If I go back to sound out, I have out 1 and out 2. So let's start by cabling those things up. By the way, in this case, right now, we're not using the input side of our scaffold. I'm really kind of just going to use the out patch in this with this particular working patch. So we'll create sound that will originate from our working patch and send it out to the speakers or to the out patch, like so. I'm going to make a send tilde object and call it out 1. I will plug that in to my first outlet, and then I'll duplicate it and change the argument from out1 to out2 and set it there. I have a third outlet. I'm going to set this up for the next patch. So I'll make a new object, and I'll make one other send object, but I'm going to give this a different naming scheme. I'm going to call this to capital ADSR. ADSR will be the next patch we make. So we have this cabled, but we haven't made a patch that receives this element yet. I'm going to go ahead and color it, though, so that you know it's going somewhere. I'll just give it like a yellow for now. I think that does it. For now, we're really just going to send sound to the outputs. And in order to do that, in order to control this mixer or this matrix, we need another object that'll do the job. We need an object here called matrix, there it is, matrix CTRL, or matrix control. Now I'm going to do this a couple times for you. If I just initialize the object like this, you can sort of see what it looks like. This object actually is an object where you can, if I lock the patch, just switch things on and off like this. So what you see along the top, the sort of positions across the row from left to right are analogous to these input positions to the matrix. These are the inputs going from left to right. And then the sort of columns, or the sort of numbering of things that happens vertically, represent the outputs. So in our case, we have 6 things that we need on the row, and then we have 3 things that we need along the side. And we'll make a matrix control object that does this. I'm going to unlock and delete this one. As I said, I'm going to do this over again. Now the way I like to do this, since it's a interface object, is I'm going to just make a box that shows you what to type in the object box, a comment rather. So we're going to have matrix CTRL, but a number of arguments, or in this case attributes. I'll make the @ sign, and I'll have a thing here called auto size 1, and then another one here called columns 6. So you can imagine I'm going to have 6 inlets that are functioning as those columns, followed by rows 3 and dial mode 2. And this is what you can literally copy and paste inside of an object box. You should only really have to type this out once, but notice that I have those little brackets on the ends. Those brackets you won't need. I just use that to show you this is how I type out an object. So if you click in here and Command C, then you make a new object box, Command V, and then you can eliminate these little brackets on this side. There's one. And if I go over to the other side and eliminate the other thing, I've got the matrix control object with 4 different attributes that will change its behavior. It'll auto size itself, it'll have 6 columns, it'll have 3 rows, and it will be in something called dial mode 2. So if I press enter, I get what looks suspiciously like just another one of these matrix control objects, but it will behave a bit differently. Here, I'll put this thing off to the side a bit because I'm going to add more comments. Now in order to make this thing function, I'm going to take the first outlet of matrix control, create a patch cable, and I'm going to swing it up here to, it looks a little weird right now, but the inlet, the first inlet of matrix itself. If I just release it here, they're connected. Now, this looks a little bit weird from a Mac standpoint, but to make this a bit more clear, I'm actually going to click on the patch cable, and then I'm going to control click on the patch cable and select something called route patch cords. And that just sort of cleans up your space a little bit. This is a great tool to just clarify where the cables are going. So you can see, all right, the output of matrix control is headed back up into the input of matrix, thereby controlling the behavior of the matrix. So we can label these now. I'm going to create some comments here, and I'll say inputs. And I'll just put this kind of up here somewhere. And we might as well just go ahead and number them. Here, I'll I'll just make this bigger. And then I'll say 1, 2, 3, 4, 5, 6. More or less have them evenly spaced out. So we have our 6 inlets, which are the waveforms. And then you kind of can see where I'm going with this. The outlets will be over here, right? So I'm going to make a left and right outlet. In fact, here, just to make sure we know what we're saying, the left outlet is out 1, the right outlet is out 2, and this one, the third one, which we haven't used or talked about much, is 2 ADSR. So these are our 3 outlets, there are inlets, and that's the definition of the object. Now, just so you can see what's happening, if I make a little message box, remember that letter M that I was telling you about? Make it a little bit bigger. If I connect the outlet of the matrix control to this inlet, the cold inlet or the right inlet of the message box, then you can see the types of messages it's sending to matrix to the matrix tilde object. I told you this was in something called dial mode. So if I grab one of these inlets and just drag up a little bit, do you see that there's a little bit of like a pie chart starting to be made here? That's opening up a gate. It's opening up signal number 2, the triangle waveform. This is number 2. And it's sending it to output 1, or the left side of the stereo. And if I pull up more, I can increase or decrease the volume that way. I can do that with other waveforms too. As a matter of fact, why don't we start by synchronizing all of these guys? So if I move this number box once again, why don't we start with that 440? I'll just type it in my F frequency box here, and I'll just bring up 1. There's an A440. That note is an A on the piano. And you can hear what it sounds like on the left, but if you want to hear it on the right, you can, whoops, I'm just having trouble dragging it all the way down. There we go. If I want to hear it on the right, I can take that same column 1 and increase this box, and now I have it on the right. Right, because it's going to the output patch, out 1 and out 2. If I want to mix other waveforms or listen to them, I can audition them individually just by manipulating this little object here. So we know what a sound, we know what the sound of a simple sine wave is, but we can also compare that to the sound of a triangle waveform. And now you might notice they sound different for a reason, and they also look different. When you hear a sine wave at the same frequency, you're actually only hearing one peak here. And if I compare that to the triangle waveform, you're hearing kind of a buzzing sound, right? Well, you're actually hearing the interference of all these other harmonic partials. These are actually harmonics of the fundamental that you see here farthest to the left. So the idea is that the frequency all the way over to the left is going to be your fundamental frequency, the lowest frequency. And then these other frequencies that happen on top of it, these are higher frequencies, those are going to be a little bit more, they're going to add sort of spice to the sound. They're going to add rich harmonics, as we like to call them. Go ahead and do this. Compare this with the other waveforms. Here's a sawtooth waveform, number 3. Tends to sound buzzier. Whoops, turn it all the way off. And then a rectangular waveform, number 4, followed by just the noise. You can see how they compare to broadband noise structures and how white noise compares to pink noise. Also, you can put them in different channels. So if I want to listen to the sine wave on the right, I'll open this gate a little bit. And then I can also patch, for example, to compare them, the triangular waveform on the left, or rather, this is on the right and this is in the opposite channel on the right. So now I have 2 waveforms on my left and right. And I can mix them together, I can duplicate them. Let's take the sawtooth waveform, for example, here on the left, and then the rectangular waveform I'll put on the right. Whoops, open it up a little bit. You can get them to be approximately the same volume like this. And you can hear sort of the consequences of their timbral differences. Now let's go ahead and define them a little bit here. So, I'm going to make some comment boxes up here. This is a sine wave, farthest to the left, right? And we might call this pure. This is like a single frequency without the interference of other frequencies. it has no artifacts or no unwanted or unplanned sounds in it. It's almost ideal. It's like something that doesn't exist in nature. It's kind of an ideal singular sound. It's good for working in a lab, but we just never encounter it in nature. It also has no harmonics, right? We don't see anything on top of this single peak. So right now it's a very simple waveform, and it's a good one to start with. So how do we define that against the triangle waveform? Here we go. Triangle wave. Well, it includes harmonics. It actually, you can't really see it too well in this view, but it only includes the odd numbered harmonics. So that would be 1, 3, 5, 7, etc., etc. And it actually, you can hear that before you can really see it here. The characteristic sound of a triangle actually has been said to sound, say, sounds more like a clarinet. If anyone has heard a clarinet, clarinets are actually, they've been engineered to sort of bring out this kind of timbre, and they tend to sound like triangle waveforms. They are occupied by mostly odd harmonics in their frequency spectrum. So that's kind of an interesting way to think about a triangle wave. Also, another property of this is that the high harmonics, harmonics roll off steeply, you could say. So, a few properties of the triangle wave. You can see that they start to get very soft very fast. And by the time you get up to this part of the spectrum, quite high, they're barely even there. And you can actually hear the difference between that and another rich waveform full of harmonics. So the next one, this next one here, instead of triangle wave, this is the sawtooth wave. And this includes all harmonics, odd and even harmonics. And you can even say that it's therefore richer in harmonics, maybe more rich in harmonics as a result. Because it is so rich in harmonics and includes all the even and odd numbered harmonics, it's the basis for a voice synthesizer. We'll make a voice synthesizer in here in a few weeks, I think. And you'll be amazed just how we can take this very simple sawtooth waveform. Again, this is number 3. Put it in both channels for a second. You might ask yourself, how do we take something like that and make it sound like a human voice? That's an interesting problem in synthesis. And when we start talking about how things work in systems, you'll get to see just how we can take that sound and sort of carve out of it the sound of a human voice. So that's your sawtooth waveform. The next one is the square waveform, or rectangular waveform. It includes odd harmonics. And the difference between this and the triangle wave is that the high harmonics are said to roll off gradually. So you might compare this spectroscope to this one and notice that the sharp decline that you get here in your triangle waveform isn't duplicated so much here. This first harmonic, the fundamental, or yeah, I should say the fundamental, not first harmonic, but first partial. This one that's closest to the left is the same amplitude, but the others roll off steeply, and then in the square wave, roll off gradually. So you might understand from that there's going to be much more sort of interference of other harmonics, or what we actually sometimes call this distortion when it's unwanted, a harmonic distortion. And it's the basis for things like guitar pedals, harmonic distortion. Let's say basis for harmonic distortion. Whoops, I keep misspelling harmonic. Harmonic distortion. Basis, whoops, I'm misspelling everything now. Basis for an electric guitar sound. So square waves do a lot for us, but that's just one quick example. Now the other waveforms here are not really pitched waveforms like I was saying. You already know this one, white noise. What this means is you have equal power or amplitude across all frequency values. So different ways of saying that. You probably heard some version of that, but you can see it, right? You don't really see it from this waveform, but what you can see is that it sort of chaotically is moving between different sizes. You can kind of get that from here. The frequency values are all mixed up. Sometimes when the frequency is low, you get big spaces or gaps, but then when the frequency is chaotically changing to high frequencies, they seem to be squashed up in the time view. But more descriptive is here in the spectroscope. In the frequency domain, you pretty much have a straight line. There's no roll-off in the way that you see this. You can't even pick out really individual harmonic partials here. Instead, you have everything at once at the same level. That's actually a lot of energy, and noise can be kind of piercing if it's too loud as a result, because you have all these frequencies at the same time. How about we compare that briefly with the idea of pink noise, which is said to be equal power across all octaves, which is something different. That means the higher frequencies decline. And you can see that here. There's like a little bit of a slope. They decline at a rate of 3 decibels, or minus 3 dB, per octave. But the point is what do we use this for? Pink noise is a really helpful reference signal for mixing in audio production. There are a lot of uses for these two different types of noise, but what I mean by that is that it's closer to the human ear's response as a result of measuring in octaves. It's a basic sort of perceptual difference between one form of noise and another, and we use this as a testing signal. We use this to say measure how good are our speakers, or how good is our mix, and how balanced are things within that mix, because the lower frequencies in fact should be louder than the higher ones. So it's a good test signal for a number of reasons. So for duty cycle, I'm just going to grab one of these receive objects and duplicate it, because I don't want to have to make colors all over again. And I'll just quickly change the R to an S to make it a send object. Oh, and by the way, maybe in addition to this, I'll just clearly say frequency in hertz, cycles per second. Duty cycle will be slightly different. What I'm going to do is connect another one of these F boxes. They're kind of the same thing, so I'll just duplicate that. And the duty cycle, what this means is, let's see here, from a value of 0 to 1, it slants the waveform left or right. It alters the timbre as a result, the timbre of the waveform, the sound color of the waveform, because the harmonics change with different slopes and sharp turns of the waveform itself. Here, this is getting to be a little paragraph here, so I'm just gonna change things around here a little bit to make it slightly more readable. So what I've done here is I put the duty cycle value at 0.5, and that's actually the default value. So when you create a rectangle waveform, or when you create a triangle waveform, it's actually implicitly got a value of 0.5 internally within itself here. And that puts the duty cycle straight in the middle within its range from 0 to 1. Let's see what that does. In order to see what the consequence of changing that value is, I'm going to slow this waveform down to about 20 hertz. So I'm changing the frequency to 20 hertz, and look carefully at these two scope objects here. Right now we have a nice little triangle wave going on here. If I take this value of 0.5 and if I slow it down by dragging down on this thing, I'm going to make it closer and closer to 0. Look at what happens to this shape. If you notice, it kind of slants the triangle. It looks more like a straight line on the sort of left side of it, and then kind of like a sharp decline going down there on the right side. Also, if you look at the square wave, it kind of elongates the segment of the waveform that is high, where you have value up top and not on the bottom. So you see like the waveform comes down and then quickly comes back up for a longer segment on top. If I then change this and make it closer to 1, I'm going to drag up past 0.5 and just kind of make it kind of closer and closer to 1. Maybe we'll just leave it here for now. Look at what's happening. Now the slant is on the left and the sort of sharp decline happens on the right side of the triangle waveform, and instead of a long high segment, we get a very short high segment and a very long low segment of the square waveform. So it's kind of like the opposite in both cases. Now, that's what they look like, but why don't we listen to them? I'll put this back in the middle, and I'm also going to raise the frequency value to a higher value. Let's put it back at, instead of 440, let's say 220. That's the A below the one we had started with. So I'm going to take the triangle, which is our second inlet, and I'll patch it to the left speaker. Nice little clarinet tone, right? Now, let's change the duty cycle a little bit here. I'm going to first make it closer to 1, gradually dragging down. Now, do you hear and see the difference in tone? You can even see what's going on timbrally here in the spectroscope. You've got more hills and valleys. If I increase it, it kind of creates more hills and valleys in the audio spectrum. If I keep going to the other side of the triangle waveform, closer to 1, we get something kind of similar, but it's kind of like just the opposite shape. It's sort of symmetric on both sides, the waveform. And it's sort of more fun to play with the change in timbre you get just by hopping between the two. Now here, I'm going to take out the sound of the triangle waveform, put this back in the middle, 0.5 duty cycle, and now I'm going to actually patch the rectangular waveform here, which is 1, 2, 3, 4. Input number 4. I'll patch that. In this case, I'll just patch to the right. Or, by the way, if you want to hear it in stereo, you can increase a little bit both. There's the right, and here's the left. And now let's also experiment with the duty cycle. So if I move this down, you see it closer to the 1 you get, the more high frequency content you get. Very similar to the triangle wave, but since the triangle wave slopes off quite quickly, you don't hear the consequence of this as readily. Instead, you hear these high harmonics more pronounced in the waveform. You can actually hear that tinginess or that bite or that buzz. That's the consequence of these high harmonics having higher amplitude. And if I swing it back over to the other side, now we'll make it closer to 1. Kind of has a nice ring to it, you might say. And it's fun to play with it, just the movement itself. And as you might see, you can get smoother motion if you drag farther to the right. You can get smaller decimal values. And things don't sound as choppy. In fact, here, if you take this number box and just drag the handle over and over to the right a little bit more, you make spaces for more decibels. So if you click over here somewhere, look at all that. You can't even hear it, it's so small. But if I move over here a bit, in other words, if I'm changing by small amounts, I get smooth timbral morphing from one type of waveform to another. So here, I'll go ahead and put it back in the center, 0.5, and just close these gates a little bit. Start from 0 here. You can and should experiment with listening to and comparing these waveforms a little bit. One last thing I will say is there's this sync input. So if I take the receive object here and duplicate it, there we go. I'm going to make a send object that corresponds. And now I'm going to send a value to the sync outlet, but instead of sending a single number like this F box, I'm going to create a phaser tilde, which is another type of sawtooth signal. We'll see which one it is in a second, but I'll patch it in. And I'm going to actually create two things here. I'm going to make a message box, M, and I'm going to put 0 point in there and connect it to the right inlet. And in a comment here, I'll just say, first of all, this is an M for message box. And this restarts at phase of 0. So if I click this little 0, it's going to actually resynchronize both of these objects. I can also add a number box here, another F, just like the others that you see. And this guy is the frequency of the control signal, or the sawtooth phaser. I'm not going to spend much time on what that is, but the real thing is if these two things get out of alignment, the rectangle and the triangle, you can actually reset them by clicking this 0, and then they restart their waveforms at the same time to keep them in sync. That can be useful in some applications versus others. And we can build larger synthesis structures with these raw materials. One thing that we can do with these at the outset, though, you might notice that it doesn't take much time to like put one of these on and then get really bored with it because all it does is oscillate. Remember that all the things you're seeing here in the red, these are all essentially oscillators, and they just oscillate forever unless you do something with them to create and sustain interest, musical interest and otherwise. So why don't we do that? Let's take this sound, whatever it may be, and we'll make a little object, or rather we'll make a little patch that shapes this sound in some way. So I'm going to leave this open, and I'm going to create the other of our patches today. I'll go to File, New Patcher, and I'll save a new patcher in the same location. I'll say number 2, and we'll just call it ADSR. And you can version it if you want. I'm only going to make one version, by the way. ADSR version 1, whatever. ADSR is a special term that we use in synthesis, and it means the following here. I'm going to bring up a little graphic for you. ADSR stands for attack, decay, sustain, and release, and it's an envelope. You can see it's a kind of a function, and we call these functions envelopes in synthesis because it tends to look like the triangle side of an envelope that you close and you lick the thing and put the stamp on it. That's actually why it's called an envelope. However, what this represents is the event of a single note. So those oscillators will go on forever unless we do something to change their volume. The ADSR envelope applies a kind of function or a curve that generally takes the shape to start and stop the note. So if you look at the y-axis here, we're calling this amplitude or loudness, and time is going from left to right like usual. And what's being called key pressure here is like if you have a keyboard or something, the moment you put down a key, it starts this event, this envelope, where volume rises from 0 to some maximum level, and this is often called the attack portion of the envelope, or A, and then it comes back down during a decay period to some sustained constant level, where you might think of the note as ringing or just kind of being held for a long time at the discretion of the musician, or perhaps as long as the note should last in the music, and then release. So the note has to come back to 0 in order for it to end. You might notice key released here. So if you are working with keyboards, this is all working in the background. You have the key coming down. When you press the key on your piano keyboard, you have the attack portion. It comes up, it goes down, it sustains, and it sustains until the moment where you release the key. When you release the key, this portion of the waveform zeroes it out again over some length of time of your choosing. That's what an ADSR envelope is, and we're going to make one in our new patch. So remember, we made this send object over here, the send to ADSR. Let's go ahead and copy that. So in an unlocked patch, Command C, and then in our new ADSR patch, unlocked, Command V. And I'm going to change send, to receive, receive tilde. And now I can receive that waveform. If I mix it using the matrix control, I can receive the waveform over here. The way we will use this information is as follows. I'll make a scale object or multiply two signals. So this was, Shift 8. And actually all I need to do is that. I'm going to connect this like so to the right inlet. And you know what? Just so we can see what's happening, I'm going to make a live.gain object. You might remember that. And actually here, I'll also give this an attribute. I'm going to say @channels 1. I only need one channel in this point. So I'm going to go ahead and make that a 1-channel live gain and just plug it in here so we can see what's going on. But I'll also go ahead and scale it and send it to my outputs. So let's also make another scaler, but I'll multiply this by 0.707. If you remember from our last working patch, that's kind of what we do to distribute this evenly over two different channels. And I'll send it to out1 at the same time that I send it to out2. So we're getting our little structure set up here. Now, how do we create the envelope, the ADSR envelope, whose shape you just saw? I'm going to use a new object in here called function. Whoops. Function. Hope I spell things right. This is a breakpoint function editor. When you click enter, it becomes your user interface. It's one of those. So I'll just add the comment here so you can see this object is called function. Here, I'll just make it a little bit bigger. And it's got a number of outlets, but I'm going to connect its second outlet to an object called line tilde. And you might know this, but the line tilde object just creates line segments. It ramps up and down according to the shapes you put in this little function box. So I'm going to take the outlet from line, the left outlet, and plug it in here. And this will be used to scale the amplitude of the oscillator signal, which we will receive on this side of the patch. So what does all this mean here? I'm going to just put this down here a little bit. Let's make some comments and illustrate this. This is going to be like time starts here on the left. It marches forward. And ultimately, I arrive over here on the right with some value that the function object will just call domain. On the opposite axis, on the y-axis, I have a high value of 1, and down here, a low value of 0. So my y values are scaled between 0 and 1, and I have 0 to some value in time, which expresses like the length of the note or of the event that I'm creating here. And we can change these dynamically. I'll start by locking the patch, and I'm actually going to just click somewhere and make a point inside of my function object. And it's just a point in space. It's actually got a value in time and a value in amplitude here. And I can actually drag this around. I'm going to drag it all the way as far as I can to the lower left. And that's going to be like time at 0 starting from an amplitude of 0. Then I'll make another point and just make the attack phase by putting it somewhere over here. I'm going to drag it as far up as possible. This is a value of 1. You can see that, a y value of 1. And I'm not actually going to care so much about where I put it on the x-axis, just something kind of over here-ish. And then make another point and create this sort of decay phase. This line segment will be the decay segment of our attack and decay, followed by, well, kind of a sustain. You can kind of make this about the same level as the last point, and then finally add one more point and drag it as far to the lower right as you can to create the release. Now you have a proper ADSR segment, and you can change how long in time this represents. Over here, I'll make a message box. If you remember, press M and type this, set domain, space, and then a wildcard, $1. You can patch this over here like so, and then create a little F box. So I made that with a little F object. And what this value represents here is the length of the note, or duration of x-axis. And the default value of this inside of the function object is actually 100 milliseconds. So if you load the patch and you don't put a number in this box, this represents 1,000 milliseconds, or 1 second, from 0 to 1,000 over here. I can change it by changing the value in the box, though. And in order to set this thing in motion, I'm going to type B and patch up, a button object. This is B for button. And this B triggers the output to the line object, you could say. So when I press this bang object, or this button object, it sends what's called a bang message in here, and it actually sends this whole thing out, and you hear the evolution of this over time. Now, if I do it right now, you won't hear anything, because we still need to send audio through our receive object into this thing right here. So I'm just going to briefly click back over into my oscillator patch. And do you remember that we made a third row here, and we made this send object? In order to get sound into our patch over here, we need to send sound from the oscillators over to the ADSR. And in this case, I'm just going to randomly choose here. I'm just going to take number 3, which is the sawtooth waveform, and I'll bring up the volume a little bit. Now, you're not supposed to hear anything right now, right? Because the sound is coming here into this object, but the ADSR envelope hasn't raised the volume from 0. If I want to mix some other signals, I could also do that. For example, maybe I'll put a little noise in there. Just a little noise. So I can put any amount of any signal into my receive object over here. And I've got signal feeding this object. And right now, the gates are closed because, remember, we have a value of 0 here and a value of 0 here. That means that the line segment is just going to wait on the values of 0 until it receives another trigger. So if I then press the bang button, I get this attack, decay, sustain, and release envelope that basically gives us the shape of a note. This is basically the shape that a note takes when you play it on the piano or when you play it on any other instrument for that matter. There's usually an attack portion, a decay, a sustain, and a release. And you can play with these segments. I would encourage you to compare what happens if you play this one with, say, this one. If I drag this point further over to the left with a fast attack that quickly goes from 0 to some value, it sounds more pingy or plucky, more like a percussion instrument. In fact, if what we want is our goal is to get a percussion type sound, I can further exaggerate these relationships by decreasing this relationship and making the attack portion and decay portion kind of louder and quicker than the other ones. It's a little more pingy now, and I'm creating something more like a ping. Now you might say, all right, that's kind of nice ping, but it's too long. If I want this note to be shorter, I can change the length of this by putting a different value here. Remember, right now we're hearing a length of 1 second, but what if I made this 100 milliseconds instead of 1,000? Very short note. I can even make it shorter. What if I made it 30 milliseconds and bang it a bunch of times? Now it's really percussive, right? I could also change the shape of the other segments. So what if, for example, I wanted a really long note? Let's say it's 2 seconds long, or 2,000 milliseconds. And let's say that I want a really long attack. In fact, here, let's say generally higher amplitude. And let's make the attack really long, the attack portion. Now remember, this whole thing is going to last from 0 to domain is going to be 2,000 milliseconds. So this will take on a very different character. Pretty nice. Now, this is where it kind of gets fun. You can actually create a whole variety of things if you combine changes in dynamism that you might create for your function object with the sort of volume or amplitude control, ADSR control. If you combine that with different pitches and timbres that you can make here in this patch. Right now we're listening to all these examples, but only using these timbres, 2 waveforms, and we're doing that on 1 single pitch. So why don't we try a couple other ones here? I'll bring up 4 and 2, which in this case is triangle and the rectangle waveforms. And also, why don't we raise the frequency? Why don't we make this 1500 hertz? And then we'll listen to the same thing. High pitches, high harmonic partials, as you can see here, in a nice long waveform, or we can make it really short. Again, let's try like 40 milliseconds. And at 40 milliseconds, the shape is going to go by really fast no matter what, but let's turn this back into what we had before. Ooh, it's kind of like a glassy sound, something like that. We can make a variety of different timbres and pitches and rhythms and stuff like that simply by manipulating these few parameters. One thing I want to show you is that there is a way, this is a shortcut that you should know for all the other things that we do in this class. I've shown you how to basically cable up things that I'm explaining, but you should all know how to read software documentation, and at this point in our journey, we might be wondering, well, how do I find out more of what's going on besides what Lewis is saying? Well, for any Max object that you see on the screen or in these patches, you can do this, and we're going to add this to your shortcuts menu. So watch carefully. I'm going to highlight an object like the function object, and I'm going to, on Mac, control click that object, and I get that right hand contextual menu, and see this first option, open function help, and then open function reference. Start by opening the function help, and what you get is something called a .max help file. This is the software assistance or help, or I guess they're kind of interchangeable terms, help and documentation. This is a file that describes what this function object is and how to use it. And you can get a ton of information and a ton of ideas about how to change things and sort of personalize and maybe even like make something of your own entirely by seeing what's available to you. So I've shown you a couple of the features of the function object. I showed you how to change the shape here. I've also shown you how to bang out the line segments, how to change behavior with a set domain message, but there's a ton of other things. You can even send messages into this thing to add points or change points and change the shape of what you've got in here. If you also look, you've got a number of tabs that describe uses of the function object in many different other scenarios. And you can also copy code out of these things and start with these as a sort of boiler or template for your own work. So if I go back to the main page basic here, also notice this is called the reference. This sidebar over here is actually not an inspector, but this little blue guy here shows us that we have a reference window open. References are open by default in a Max help file, and you have a list of different messages that you can send the objects. If you scroll down, you have other attributes. These are the ones with @ signs that I was telling you. You can change the behavior or properties of these objects using all these features that are available and changeable inside of the help documentation. So once again, you get that by right-clicking on an object. And once again, control-click on Mac, you can choose open function help. Now, if you want a more traditional sort of documentation, you can say open function reference or open the object's name reference. And it brings up essentially like an XML file, and you can scroll through this and read a lot more about what all those things do. It's actually like very helpful for breaking down certain details. I would not recommend starting though with the documentation like this. There's no way you're going to memorize all those details. Instead, it's actually more helpful and more fun to immediately put things into action. So I can control click and say open the object help file and immediately start hearing and seeing different ways of patching these things together. So there's a little bit of a detail for you, but that's essentially our work for this day. We have a basic waveforms patch. Make sure that you finish this and commit it and push it at the end of the week, as well as this ADSR patch that you save and commit. And understand how these are working together to get you a kind of composite sound. Couple of mistakes that I often see in this patch are like the following. Right now you don't hear any sound, and that's because we have a value of 0 here and a value of 0 there. But if you accidentally, for example, don't lower the amplitude here all the way down to 0, if it's anywhere other than 0, watch this value up here. You see X and Y. If the Y value is at all bigger than 0, I'll make it really small here. Let's say 0.26. There it is. I'm going to release my mouse, and it doesn't really look totally clear, but you can see that this value is lower. This value is not. We're going to get what's called bleed. If I press this button, do you see that there's still a little metering here, and we still hear sound actually through the outlet in our out patch? That's because when the function finished its cycle through the function object, it ended here at a value of 0.026. So there's still some signal being let through this scalar object, and we get what's called bleed in the synthesis world. We're not supposed to have sound here. This is supposed to effectively close the gate. But since we didn't close the gate, we have sound that's so-called bleeding through the gate. That's why it's called bleed. I'm going to go ahead and lower this all the way to 0 where it should be. I'm going to drag it down all the way very carefully to the right, downward right corner. And I'll run the function again. And notice now there's no metering here, and the signal clears, and I don't hear any bleed. The idea here is to always make sure that you're starting and stopping at 0 so that you have a clean event that begins and ends with silence. One other fun thing to check out here is that these don't have to just stay as ADSR curves, but you can essentially add a lot of different points and see what happens when you use your own functions. And if you read the software documentation inside of the function help file that I showed you, again, control, click, and then select the help file, you can find other cool ways of building functions in this thing. Let's make this bigger. Let's make this like 4,000 seconds. Or 4,000 milliseconds, in other words, 4 seconds. I have no idea how this is going to sound. But let's add some more waveforms in here, and why don't we change the pitch? Why don't we make this kind of low this time? Let's make it about 300 hertz. Why not? You can see it really changes the look of the waveform too. Now let's run this and see what we get. Kind of cool. Go ahead and give this a shot. Give it a, see what you can do to come up with your own kind of ideas that sound interesting here. Next time we meet, I'll show you how to save some of these values, and we'll continue building on this with new tools. But I hope you can kind of see these are the sort of basic raw components of synthesis. We're on the way to building a complete synthesizer at this point. We're getting all the sort of raw mechanics we need. We need an oscillator or a combination of oscillators of some kind. And we also need some sort of amplitude control, or what sometimes people call dynamics control. So we're controlling the amplitude of the sound with these curves at the same time that we're controlling pitch, frequency, and timbre using the oscillators. And those are the first two major components that we need. So with that, have a great day, and I will see you on Wednesday, hopefully in person this time. Again, reach out with any questions. Email is fine. I'm planning on doing office hours like normal on Wednesday. Stop by, say hello, and write to me if you have any questions about these or other things that have come up in class. Have a good one. Bye-bye.